Welcome to IBM Skills Academy Data Science Workshop. This is Lecture 2, Data Science Methodology. In today's lecture, we will look at how data analytics can be applied to business through the fictional example of the Chicago Bike Share Company, where we will look at such concepts as descriptive analytics, predictive analytics, and diagnostic analytics. And lastly, we will do a comparison of 3 data analysis frameworks. Now here is your instructor, Armin Pistochian.
Ladies and gentlemen, welcome back. Lecture 2, Data Science Methodology. Slightly different format from what you've been watching thus far, but let's begin. Data analytics in practice. Dan Van Zet, who's the Group Vice President at the Analytics Information Management at IDC, he's been known for saying that in recent years, all headlines about big data, business, intelligence, performance, and so forth, they all have diverted our attention from the ultimate reason from having these solutions in the first place, and that is decision support. I want to go a step even further. If you get a chance to listen to IBM CEO Jeannie Rametin, she doesn't use the term AI as in artificial intelligence. We view this as augmented intelligence. This entire modeling, data science, machine learning, prediction that we have at our fingertips is not here to supplant, to replace, but merely act as a second opinion. It is here to augment, to add, to help us in finding those insights and making sound decisions regarding the organization that we're in. Let's take a look at the data analytics lifecycle. You see here that we have broken it into 5 distinct life cycles. The first one is, well, what is your plan? Understanding the status of your business. Let's move this over here. You'll note that a lot of the design thinking approaches that we use actually hinge very strongly upon this stage of the planning. Once we get an understanding of the status of our business, what it is that we're trying to move forward with, what pain point we're trying to address, we're going to ask the question of what happened, the data analytics. Identify what happened and determine how to perform against that plan. The notion of analytics, whether you're doing descriptive analytics or diagnostic analytics, really, especially in the case of descriptive analytics, also known as descriptive statistics, it's when you are working with a population and you want to see deviations from the middle. You do calculations such as variance, you do mean, median, average, and see how far off and how the data that we have, just how exactly can we describe it through certain charts and so forth when we do a preliminary visualization of that. As we move forward to life cycle, the third part of this, it's diagnostics. I think what did happen? Diagnostics is why problems happen and try to identify key patterns. Perhaps this is where we start to look for anomalies, outliers, to try to see if they had any bearing over the just what it is that happened, as we answered in the earlier part of the life cycle. Then we move into predictive analytics. What happens next? We use patterns to predict future trends. You know, if you really think about it, machine learning solves 3 types of problems. And then this is very much an area where we start to work with models and machine learning. It can predict, classify, and cluster. And so the data that we have typically would fall within one of these 3 tasks that we're trying to do. As we move past predictive analytics, prescriptive analytics has gone beyond the notion of saying, well, I saw a pattern, this is what seems to be happening. I can predict that, so it's these other events with a high likelihood, confidence. These are probabilistic systems, may happen in the future. But now comes the question of, well, great, what do I do about it now? You know, if a certain company is having massive amounts of employee attrition, this actually happens to be one of the labs that we will embark upon. Well, could it be that distance from work is a determinant? Well, great. That might be what happened. We could predict that if we keep this up at this rate, our offices, our cubes are going to be empty. It's a lot of HVAC, a lot of food and so forth that is not going, we have to readjust. So prescriptive analytics starts to address the question that perhaps employees should work from home, those who happen to be 20 miles or so away from office. Of course, this brings up the point that those employees who happen to be 5 minutes walking from the office might say, hey, I want to work from home also. My colleague is doing exactly that. So it's very interesting as we move into the prescriptive part of it and trying to answer the question of, well, what it is that I want, what should I do now that I have my prediction, now that I understand and I have my diagnostics. Let's take a look at a bike sharing example and see how we can run this life cycle through a hypothetical situation. Here we have a business analytics, station revenue and utilization. This is a video. I encourage you very much to take a look at it. It captures most of the story. I'll let you go through this at your own turn. So here I'll give you a recap. We have a Chicago-based bike sharing company, and it offers bike rides around the globe. Interestingly enough, if you note that the scooters, the electric scooters are the big thing, especially in San Francisco area, and perhaps at the West Coast here where I am in the Northeast area in Boston, it's mostly electric bicycles. Europe has the bicycles more prevalent than the scooters for their sharing, ride sharing, if you would, approach. So in this particular company, we have noticed that in October, we had just over 42,500 rides in October. The entirety of rides that we had in the year of 2017 were just over 500,000. And the total lifetime rides since the bike sharing company was incorporated, really from 2014 until 2017, has been just shy of 6.5 million rides. Very well. So these are case studies. These are just the data points that we have collected thus far. So the first question that we want to ask, what is our plan? Now, planning relies on these 4 key steps. First, it requires an understanding of past performance. And again, this is where design thinking methodologies can really help us in gaining that understanding. It involves identification of deviations from the norm, plan versus actual. Are there any outliers in here? Evaluation of possible scenarios also is very much part of the understanding that we want to gain at this very earlier stage. And a lightly put, if you would, prediction of likely outcomes, an assessment of risks and constraints, perhaps more so on a financial setting at this stage. Very well. Now, the business understanding, what is our plan? We want to understand the budget constraints. We have revenue forecasts, and we want to compare these against our revenue forecast. We want to perform a demand planning and supply chain optimization for the bikes that happen to be in different regions. Who knows? Maybe it's socioeconomic disparities, could be weather-related events. Maybe the bikes in San Francisco, as you recall, it's a lot of hills, so that might have an impact where the bikes are congregated. So we want to increase our revenue, we want to reduce our cost, and we want to maximize our finite resources that we have. Those bikes need to be where they most demand and not wasted, nor at a situation where the demand has outgrown the supply and people are looking for bikes and there's none at the corner to be found. So what is our plan to gain a business understanding? We're noticing that quite a few, our optimization is at $500,000, and our budget was for just under that. But if you notice, there's a big, huge variance. The actual, we had budgeted for 3.5 million volume of bikes, and the actual ended up being 3.1 million. That's 11% of a variance, of a shortfall. So our Q2 revenue targets were off by 11.8% overall. What else are we noticing in here? Notice this is our marketing campaign that we have run. Our actual plan was to spend just over 8 million, and now we have the budget was 8.8. There's a variance of 9%, just over 9%. So the Q2 revenue targets are off by 11.8%, and the marketing spending is under budget by 9.13%. So we are gathering our plan, which is in the earlier stages. Let's answer the question of what happened. Let's do a performance analysis. Let's take a look at the state of the business metrics that we have. Identify the data that is required. Weather might be one. This might be a place that we start to see that really peripheral data sets, events are impacting our revenues and our actual versus budget. We need to extract and prepare the data. Frankly, data preparation and extraction happens to be one of the most arduous tasks of a data scientist, and the most time-consuming one. Throughout this journey, we will come across certain labs where we do a lot of data refinery work. You will really get to enjoy the tool set because it has totally streamlined and made it so much more easier for the analytics, the cleansing, the wrangling of the data to take place soonest. So we can start to begin predicting and using models and deploying those models. We'll need to analyze data and, of course, present data. A bit of a visualization comes into handy in here. A lot of data scientists now use Jupyter notebooks, and they use a lot of visualization tools that are open source. Matplotlib, Brunel, Bokeh, PixieDust. These are typical visualization tools that gives us still a sense of our descriptive statistics. Bar charts, pie charts, and scattergrams, and so forth. As we delve into our performance analysis, we're asking the question, what happened? Well, the Q2 revenues are down. And what do we need to do at this point? We want to ask questions to understand the history. Since 2014 until 2017, how has this portrayed as the years have gone by? Is there a cycle? Is there a pattern? Identify past issues. Interact with data to ask new questions. And the whole idea in here is to be able to find answers quickly because a lot is at stake. Bikes are being wasted in one location and in other location overutilized. what happens? Performance understanding. So we have a dashboard. We're able to do some visualization, and we are starting to notice some interesting patterns in here. For example, our actual of 7.8 million is pegged against a budget of 8.7 million. These are revenues. There's a variance of 10%. 10% below plan is what our revenue, that's what our graphics has shown us. Let's delve deeper. We're starting to see that 4 out of the 6 months thus far, it has underperformed. January was one of them, March, and May and June. Let's take a closer look. Now we are able to actually break down to the various districts in Chicago. Districts highlighted in blue are underperforming. There's the actual revenue, there's the budgeted revenue, and the variance. So what happened? Let's delve into the performance understanding in here. A good way to do this is to actually plot your data on a map. You can get a lot of map renderings. One of my favorite tools is Matplotlib. It's an open source tool. You can import that into your Jupyter notebooks and align the data against the coordinates on the graph. We're starting to see some interesting things in here. For example, notice that the bike shares around the revenue are actually around the world are actually measured, in this case in Chicago, by the location that they are. So location is a key determinant in this sense. Some stations have over 90% utilizations with no bikes left. Some stations have absolutely no bikes left on the weekends other than on the weekdays, others on weekends. Without enough bikes to meet the demand, the company is losing revenue opportunities. Very well. Let's move forward. What did happen? We want to uncover details such as the frequency of the events, the cost of the operation. What is the root cause of failure where at certain locations we're running out of bikes so quickly and people are still clamoring for one. And in other locations, the bikes are strewn and it's not being used, underutilized. Is there any casual relationships? Casual relationships are those that we didn't quite think of or plan of. Maybe it's the weather. Maybe it's the hills on the street. Could be safety of the neighborhood that's causing such concerns. Then let's delve deeper. Identify the business causes. What did happen? We need to get to the bottom of our revenue problem and understand the real drivers. We have to set aside our own assumptions and find accurate solutions quickly. So there's a lot of biases that we can carry with ourselves. You may argue, is it the data that harbors that bias or the algorithms? This is exactly why we need this rigorous life cycle, which is exactly why we need the approach of design thinking to be able to filter out the human bias, the data bias that is involved with gathering and predicting the outcome. We're seeing some interesting things in here. We see that all of our valuable data, including weather information. So as we juxtapose the weather information over our data, we're noticing that the top drivers for the number of rides are temperature range and the month, as well as humidity and dew point. these happen to have a rather large measures of the human humidity, dew point, and temperature, the uncomfortableness, if you would. Let's now plot our bike sharing activity against the weather, against the precipitation. Interestingly enough, we're starting to see a somewhat of a correlation between the bikes used and, of course, the months at hand. Seems that September, October, in this case, we're seeing July, August. Again, in this case, we're seeing July, August, summer months clearly are causing a greater spike in our bike shares being moved out. And the question is, how can we maximize this? Let's use some predictive analytics. Predictive analytics now starts to work with machine learning models. When you work with models, really, you end up having to use various types of data sets. A certain group of data sets you would use for training. Other data sets, not seen in the training data set part, is for test. You don't want to mix these two. You could have something known as overfitting, where it starts to predict very accurately on its own data that it has seen. And then when you give it a brand new data point not seen before, it predicts horribly. That's an overfit. So as we delve into predicting using data models, we start to think about identifying some of the business outcomes that we would like, determine data required to train the system, the types of analysis that we want to run. We have to validate the results, test the predictions. Again, this harkens back to the notion of having a training set, test set, and frankly, feedback set, or as they are also known as a double-blind study. Data points that are unknown to the human and to the machine. And let's see how well it predicts based on the patterns that it has learned, or how well it clusters, or how well it classifies. These are all the constructs of what a machine learning model would do. So, all right, now that we're working with our predictive models, what happens next? We have identified an issue with the bike supply in downtown. We've discovered that the issue is causing revenue loss. Used all relevant data sources to assess that weather is the driving levels of demand at different stations. So weather ended up being that peripheral, that side data point that we didn't have at first in mind when we started collecting the data. So what we need to know is to predict future demand for bikes so we can plan our supply accordingly and maximize the revenue while taking all variables that may have an impact into consideration. Neighborhood, location, weather, or the streets hilly, and so forth. Is it near the big body of water? And is it too windy where we have amassed our bikes to be shared? Now we're starting to see some interesting results. As we build our dashboard, we're starting to see that weather is becoming a key player actually within our bike sharing. February 4th is the 5th, and this is just a very slight time series that we have taken in a shorter time span. See if we can get further insights. Solution optimization. Once we have gone through the rigor of what a design thinking would do, would help us in coming up with our plan, realizing using descriptive statistics to explain and show, visualize what it is that happened. Continue with predictive models with predictive models now, tasks such as regression, linear regression, logistical regression. These are the key points that help us go past descriptive statistics into inferential statistics. And of course, the entire idea is to then become prescriptive. How? What is the one or handful of actions that I need to do to make my desired prediction come true? It's one thing to predict that how many employees would leave your company if you carry on with your means and ways by next month. It's another thing to prescribe and say, okay, why don't everyone work from home on Fridays, for example? And the means and ways that really is egalitarian and helps maximize the reason for having that building over there. And as we delve deeper into solution optimization, what is it that we should do? Identify an issue with the bike supply that's in downtown. Discover that the issue is causing revenue. It happened to be weather related. We can run predictive analytics to identify future demand. And now we need to enact an improved business plan that optimizes bike allocation on a day-to-day and location-by-location basis. Here's one other way that as we start to categorize this within different regions in Chicago, we're starting to see, for example, that the near north side, 287 bikes, being up over here, downtown at 282 bikes, and near the west side, we have 226. There are sufficient bikes in the fleet today to meet the expected demand. Or it may be that we probably would have to move some bikes that were congregated needlessly in these other regions. The system recommends the amount of bikes needed to satisfy the predicted demand. In this case, downtown will require 82 extra bikes. And we move them from these other regions. Very well. Let's discuss data analytics methodology. Methodologies as a whole, whether you're working with an AI lifecycle and pipeline or data science methodologies, they provide a framework for how to proceed with whatever methods and processes and overall heuristic approaches that one may come across so we can obtain our results. It provides these guardrails, a way of thinking, a way of approach. And data science most certainly has one. In fact, the majority, all of the labs that we do, the 8 lectures that follow, and the labs that go along with them, they are governed exactly by the methodology of data science, in which we will see shortly. Here are some existing methodologies. These you have heard and seen before. CRISP-DM, cross-industry standard process for data mining. Notice this is not an IBM thing. This is an industry standard thing. It begins with understanding business, understanding the data, preparing the data. A lot of data cleansing goes in here. This should be a huge box. This takes the longest time. The modeling, evaluation, train, test, and the deployment of the model. And this is a cycle. As we gain a new data, we continue, we iterate, and we deploy our models as it may have changed based on the newer understanding. KDD, knowledge discovery in databases, is also another methodology long used. Notice the data selection, the processing, the transformation, the data mining. And these over here again speak of data wrangling activities. Sample, explore, modify, model, and assess is another methodology that's being used. SAS is being used. SAS is also used a lot in medical applications. Now, there's something quite interesting in here. All of these happen to share one thing. They all have one thing in common, and it has to do with the type of data that goes into the system. Let's chat more about this. Rankings. CRISP-DM is a prevalent methodology used by most orgs. CIMA, KDD, some of common characteristics, data gathering, data transformation, modeling, evaluation. One difference is that CRISP-DM includes business understanding. But what is really fascinating, the very one thing that all of these approaches shared, is that they were founded on structured data. CSV file, Excel spreadsheet, data that resides in databases, IBM DB2, Microsoft SQL Server, Oracle. These are data points that they reside in a table, and you can call upon them with a SQL call and find out further insights about them. Now, the need for the modern data scientist goes beyond working with structured data, CSV files, and Excel spreadsheets. The data scientist, we need a methodology, not precisely that of CRISP-DM, but one that caters to unstructured data. What has brought forth the modern data scientist, what has brought forth the crossroads of machine learning of data science, is not another CSV file. It's the images, the pictures, the videos that are on our mobile devices. It is the data gathered from sensors in the Internet of Things. Data gathered from tweets, emails, all of these unstructured data. How can I gain and bring forth insights from my unstructured data? Let's take a look at a methodology that addresses that. Section 3, Data Science Method. Let's take a moment in here, and as we move from left to right, we have our business understanding. This is our current business platform, and a lot of design thinking activities are built to really address our business understanding. We don't want to boil the ocean water. Who is being impacted by this? Who are our users? Where are the pain points? We do activities such as empathy maps. And we try to move forward through the loop, as you would come to know and soon enough. And you may have already gotten an edge on this had you taken the design thinking online workshop. Once we have a better business understanding, we start to delve into the data exploration, preparation, representation, and visualization. Notice that these three buckets remind us very much of the KDDs and the CRISP-DM activities. And as we move into deploy data models, validate, train data models, and the feedback, reiteration, is where we're starting to use the data engineer, the data scientist. Let's take a look and see what roles are involved in here. We have a data scientist and a data analyst. They work together. There's often a business stakeholder in here who is perhaps the one with the pain point that's trying to resolve. The work of data exploration and representation is really done by all. Tom is starting to work in his Jupyter notebooks as he's starting to cleanse the data, look for anomalies, do any feature explorations, feature engineering. If you look at the table, each column, really, the column heading is known as a feature. So some of these columns are of absolutely no good. They don't help. In fact, they might even throw off our data analysis. A spreadsheet from human resources that has a column of age over 18, and all 1,400 rows are yes, 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 yes. Well, that as a data engineer, one would remove that column. That's really not helping us. Employee number, that perhaps is a redundant field. Employee number 1 until 1,434. How is that helping me? So there's a lot of work goes into cleansing the data. And the data visualizations and presentations. And these are really quick visualizations. The lab that we do with our data refinery would give you a quick sense of the description of the data, of the statistics that were involved in here. As we prepare our data and we're satisfied, and we start to now train our data set using various models. If your data set is a yes or a no, would the employee stay, would the employee leave, it's a true or a false. Basically, if it's dichotomous by model, we use a binary classification. Logistical regression comes in handy. If you have yes, maybe, no, well, that's more than two. Now we use multi-classification approaches. Random forest trees often come in handy with this type of approaches. What if it's clustering? What if you want to cluster your data? These bunch of data points look like an alligator, and these are crocodiles. Well, we may not have named them because it's unsupervised learning, but we want the system to build a model that can distinguish between these data points without me having to label what those are. That's another approach that's the model that's being used over here. Neural networks does really well. We're working with those data sets. Now we need to validate our data models and finally deploy them. This is not a one-time. Questions that you would ask of yourself during the feedback, during the data deployment model is that, how often is my data changing? Is my data static or is it dynamic? Is it the Twitter feeds that I need to be on top of perhaps every hour? Maybe if I can get ahead of the sentiment on the Twitter world, I can perhaps get back to my candidate who's running for office and tell them that perhaps there's a large negative sentiment in regard to what they said the night before. So my data needs to be refreshed and uploaded and retrained constantly, really. And there are data that doesn't change that much. Every day at midnight, I can deploy my model and run a feedback and either reinforce or negate the data point that I have. Maybe I may need to reclassify. Summary of resources. In summary, we talked about the ultimate goal of the data analytics is to be a tool for decision support. It is here as an augmented intelligence. The 5 stages of the data analytics lifecycle, we talked about the planning, the descriptive analytics, the diagnostics, the predictive, and the prescriptive. Prescriptive being, so what do I do now? 3 of the widely used domains, we just got a brief look at CRISP-DM, KDD, CMAM, and we got to realize quickly that these happen to work with structured data. And we identified those blue buckets, if you would, as the modern data scientists' framework, especially when they are working with unstructured data. We have a wonderful set of resources in here. We encourage you strongly to explore them, and these will augment your understanding of Lecture 2. Thank you.
Thank you for joining us, and we look forward to seeing you at the next lecture.